steal this for a second.
So while these guys are getting set up, every once in a while the program committee gets together and tries to think of a good keynote that would come up for a NANOG. We don't do it at every NANOG. We do it opportunistically when we have some great speakers, interesting topics. So the reason I'm the guy stuck up here announcing this is that I was the guy who got Tom and Dan to actually come and do this keynote and got Amazon to present, which I think if anybody has been around to conferences for years, Amazon doesn't present very often. So it's kind of neat to get these guys here. But you've got Tom Killalea, who's the vice president at Amazon of, what do you do?
Technology.
Technology, that helps. And Dan Cohn, who's the principal engineer, right? It's all about titles, right? So anyway, these guys are get this thing all set up, and we'll have a great presentation on what Amazon is doing these days, big challenges, simple solutions. And I think they've been a pretty innovative company and been pretty flexible when we bombed and have now grown up again. So I think we'll see some good stuff. You guys ready to go? Pressure's on. There you go. You get the wrong screen resolution.
Mirroring still. You still mirroring? Am I still mirroring? You just gave them the presenter tools. I think once we do presenter tools, we're set. Okay, we got it here. Okay. Is this one live? Live? Yeah, great. Okay, sorry about the little delay. I'm Tom Killalea from Amazon.com. This is my colleague Dan Cohn, who's not quite mic'd up, but getting there.
Hi, I'm Dan.
I want to just set a little bit of context first. I'm sure you're all familiar with Amazon.com, but in terms of what we think about as our mission and what we do, what we strive to do, and this has been our mission for about the last 13 years, or 12 and a half years, is to be the Earth's most customer-centric company. With respect to customers, we think about three different things. We think about consumers, or people who buy stuff from us, sellers who sell on our marketplace platforms and so on, and developers. Now, some of our customers wear multiple of these hats. There are, people may have overlapping roles, but we think about these three categories of customers. And in terms of how we serve the consumers and sellers, our objective there is to provide a place where people can find and discover anything they might want to buy online. And that comes in all sorts of different shapes and sizes, but it essentially, from the front end looking in, looks like a bunch of websites in different forms. The back end gets pretty interesting in terms of what lies behind that. This is what an 800,000 square foot building looks like, which contrasts sharply with Randy's apartment in Tokyo that we were talking about this morning. This one happens to be out in Nevada. There are a bunch of these around the world. We've got something like 30 buildings, not all this form factor, but that's what fulfillment looks like and what makes that box show up on your doorstep. They're not just wide and deep, but they're pretty high too, quite well stacked. As you take your digital pictures, you have to watch out for crazy guys on forklift trucks zooming around. And this is where the rubber hits the network, really. This is a sortation device. You can see little people at the end of, so basically there's a conveyor belt that's going at about 10, 20 kilometers an hour with tilt trays along it. And if there's any packet loss or significant latency issues, then that tilt happens at the wrong slot and potentially the wrong product ends up in a box. With respect to how we serve software developers, what we try to do, we found that over the last about 12 years or so, we've built up a lot of useful infrastructural components that have allowed us to build the applications that we build. And what we said was really we should figure out a way to give other people access to those. So we've exposed a bunch of APIs so that other people can build web-scale computing services and free developers who are trying to build an application from the heavy lifting typically associated with launching and growing a successful web business. A lot of that heavy lifting, we refer to it internally as muck. So, anything that isn't the business logic that you're actually trying to expose to the outside world is muck. So servers, networks, cables, all that stuff is muck. And we feel like developers running startups, they'd much rather be building their application than dealing with this stuff.
This is actually not a picture of our data center, by the way.
We're slightly tidier than this, and I'm sure there's somebody like keeping their head down in the room right now because maybe it's theirs. But in any case, this is the muck we think about, and this is the sort of image that we want to be able to free developers from. So rather than have them deal with that, we try to allow them to deal with APIs. We publish very simple APIs in REST and SOAP format, and at the end of the month, give them a real nice, clean bill that looks like what's on the right-hand side here. And we start from those developers and work backwards in terms of what are the right abstractions on top of this muck to expose. So storage was the first one that we exposed. We call our product there S3 for a simple storage solution. Our computing is, we call the Elastic Compute Cloud, or EC2. Queuing is another really useful one in a distributed context. And queries as well are ways to do structured queries against those index data stores that you put into our solutions.
As you might expect, Amazon maintains a rapidly scaling network architecture, and along with the scale of our infrastructure comes the expected scale of internet egress traffic. This graph actually shows two types of services. The orange here represents our website business, which you're historically more familiar with, most likely. And as you can see, the rate of growth has been increasing over time. And the blue represents our Amazon Web Services business, the vended services just talked about. And as you can see, very recently, the Web Services business has become a larger bandwidth consumer for internet egress than the website business. And I think it's important to note that while we've been dealing with this rapid growth in the size of our infrastructure, we've also been increasing the ratio of network engineer, the ratio of network devices to network engineer. So we have fewer network engineers required to operate each device as we scale, and we get better with that over time as well.
This is an interesting graph. Websites there, by the way, is the aggregate of all the sites we run, not just things with an Amazon in the domain, but other sites we operate like IMDb and Target.com and so on. There are a number of questions that we think about as we try to build large-scale systems. One was influenced by something Jim Gray said over 20 years ago. We have a desire to be able to build planetary scale distributed systems that could potentially be operated by a single part-time operator. So as you think about that challenge, you have to really wonder, is it possible? Can we provide this muck in a way so that the developers don't have to worry about it, so that the abstractions are clean enough that you really don't care about what goes on underneath? And ideally, we'd like to be able to do it in such a way that the people who are responsible for what is below that abstraction line, the network engineers and so on, don't have to worry about the muck either. And that's really the bulk of what we're talking about today, is how do we actually make that be as painless as possible? Here's some other questions we've asked. So one of the key challenges in building large-scale distributed systems is, what do you do with your persistent state, and how do you deal with persistence and with shared data systems? How do you deal with what Eric Brewer at Berkeley positioned as the CAP theorem? So there are these three things: there's consistency, availability, and network partition tolerance. And you can only, at any given time, be guaranteed to provide two invariants out of these three things. So as you scale, you just have to deal with, how do you compromise? What trade-offs do you do? And as you all know, network partitions, they either are or they aren't. And when you're building applications at scale, you just have to learn to live with them and figure out how you deal with them. But you don't have a lot of control over them. They just happen. You have to admit that they happen at maybe the worst timed moment. Availability is something that we always strive for 100%. So as we think about, with respect to shared state, how do we manage it, we really get into, well, what can we do with respect to consistency to deal with trade-offs? And you eventually conclude that hard consistency is an impossibility in certain systems, and you have to get to a point where you deal with versioning and deal with eventual consistency and convergence if you are to be able to tolerate those network partitions. Another key challenge that we think about is dependency discovery. How do we make it real time? How do we make it something that's actually useful rather than just a bookkeeping exercise where like someone goes out and surveys and 5 minutes after they've produced the server results, it's completely out of date. So I'm going to show you something in a little while that gives you a view into what we've done in this space to actually make it real and make it useful information. And then once you pull in that and you know what your dependencies are, can you become recovery-oriented? Can you protect yourself from the downstream services and so on that you talk to and the badness that may occur there? And can you actually self-heal? With respect to the communication infrastructure then, we tried to figure out how that can be self-scaling as well, infinitely self-healing and load balancing.
Okay, and in order to make systems that are self-healing and potentially self-configuring, it's really important that we take a holistic view of our system.
This is really, in essence, on the left-hand side, a dependency map. And what it's showing is, for the invocation of a single gateway page on the Amazon.com site, that call becomes a call to sometimes over 100 different services. And so from the origin outwards, you're seeing calls to all of those different services. There's a massive fan out, obviously. The distance from the center represents latency to that service. Color represents the health of the remote service for some definition of health and its ability to respond. And at any given time, there will always be some things that are to some degree in a less optimal fashion, but it's good to know, be able to look at the fan out. And an interesting thing about how we distribute content that makes the traditional dependency mapping pretty much impossible is that all of our content is scheduled by algorithms rather than by people. So this is the dependency tree as it existed within the last 60 to 120 seconds. And it'll be different in 5 minutes. It'll be very different in an hour. And so you can't keep track of that. But if you're an operator, you really need to know, if I'm having a problem, I want to see it as it exists today, as it's being pulled out of the network and pulled out of the metric stream. And then I want to know that for those things that show up as red that I can click through and dive into and expand the tree from, I want to know that its dependencies and its lack of health represents real state within the network.
I just want to emphasize that what we're looking at here represents a call to the main Amazon gateway page. And all of the dependencies there are secondary calls that have to return before the main page is rendered.
On the right-hand side, there are some metrics showing some help of that position within the overall tree that you're at. Those metrics and what shows up there as well aren't the choice of the many hundreds of metrics for any particular service invocation that show up there aren't managed by like some master curator. They actually also are influenced by the wisdom of crowds in terms of what people find useful to show up in that position. So our challenges cause us to think a little bit differently as well about how we organize people and how we put organizations together. What we found is if we really want to strive for simplicity and auto-configurability across the whole infrastructure stack, or the muck stack as we sometimes refer to it, we need to take the different disciplines within engineering, be it network engineering, electrical, mechanical, or systems engineering, and put them together in a single organization where there's a cycle of reinforcement in terms of the work that they do, where they share objectives, they share constraints and understand the challenges that they each have to build solutions towards, and they share metrics as well, whereby a typical metric might be the cost of doing a unit of work, and we can't optimize that without having each of these 4 engineering disciplines work towards it. There are other constraints then that we work towards as well. Tim O'Reilly, in a definitional paper on what Web 2.0 is all about, he used the phrase software above the level of a single device. And that applies to pretty much everything we do. Nothing very interesting happens at the level of a single device. For that gateway invocation, with respect to what the topology looks like in a logical level is there are client requests coming in from a browser that go to just page rendering components that do pretty much nothing but that. They make requests then to either aggregator services or directly to services that might have sufficient business logic to provide a fragment of a page. And as you saw in the Maya fan out, there could be up to hundreds of distinct services called at that level. And they then may have persistence layers that might be composed of Amazon S3, some structured data store, Dynamo, and so on. Do you want to go back?
Okay. We're constrained, of course, by building applications that have to have fault zones wider than single racks. This is, again, not a picture from our data center. Data centers go away as well as racks, so we have to be able to extend outside a data center. This is also not our data center.
This one was hit by a tornado, though. It's I think it's an AT&T facility in Virginia. And I think it still looks like this 3 years later. This is a latency graph. Latency is also a considerable constraint as we think about how we engineer the network. So just to explain what you're seeing up here, you're seeing a logarithmic scale graph of a typical service at Amazon over 2 weeks. And the orange trends on this are reads, the red are writes. The lower pair of trends are the average latency, and the upper on a log scale trends are the 99.9th percentile latency. So we pay very acute attention to each of those. So 99.9th percentile is if you've taken up 1,000 observations, what's the latency at the worst of those 1,000? And paying attention to both the average or median and the 99.9 percentile makes us really focus on how do we deal with packet loss? How do we think about convergence times such that not even high percentile observations are impacted by them?
We're effectively instrumented across our stack to be able to make these sorts of determinations at the application level as well as the network level. So we're also constrained by some unusual change management rules. We don't have any maintenance windows available ever. So when we do make changes, we have to be bound by both latency and availability SLAs that are very strict. And because of the instrumentation that we demonstrated in the previous slide, we tend to notice even if there are minor perturbations in the network. We're constrained, of course, by people. We hire good people, but even good people only can do so well. And in fact, people are not great with really complex systems that involve referencing policy and process and having to repeat things many times, which is really important when you're building at scale very fast. So we have to think differently about automation in our environment. We have to build self-configuring, self-verifying systems. And we have to build those systems as building blocks so that once we get a certain unit working of, say, a rack or a data center or whatnot, we have to be able to then say, okay, we want to repeat that again. So we don't have to think about the detail work that went into defining the self-configuring system the first time. And then those blocks build on top of each other, and so it becomes easier to deal with the next level of problem, how the building blocks connect with each other, and not what we did originally. And we build APIs and self-service web pages to keep humans out of repetitive error-prone processes. Configuration of various services that would typically involve network engineers touching things, system engineers touching things. We've automated to the point that they can be called by APIs, so the standard errors are not likely to occur. We think differently about policy as well. And as far as policy goes, it's been my experience that if policy is not built, if policy isn't built into process, it might as well not exist. If policy has to be searched for on a web page, a wiki, it may as well not exist. People will follow it for a certain amount of time, but as you build up additional policies, then people tend to not look at past details. And as a result, if policy is not auto-enforced by a system, it may as well not exist. So that leads us to create systems that verify and enforce policy. And we'll talk about those in some more detail in a bit. It's important for us to make scaling really simple in our environment so that it can be defined by policies. And simplicity is not something that comes easy. Simplicity takes work, it takes iterations. So because of the levels of growth that we're dealing with, then every time we're working on small units, it's not sufficient for us to think about how do we solve the problem that's in front of us right now, but how we would solve the problem if it was scaled 10 times and 100 times. And sometimes that's a challenge to do. But doing so means that when you actually get to that step, then things work out simply as well. And really that's driven by this, which is that we need to be able to deploy production data centers, and we do deploy production data centers in 2 weeks from the time that facility is handed over to us to the time that the facility is completely full of racks of servers that are running in production, that are taking calls in the dependency graphs that were shown on Maya. That's been a big challenge and a big driver. So in order to really make this work, we have to eliminate the mundane work, where mundane work is everything that can't be easily defined by heuristics or templating. So there's the normal deployment side of network engineering, the deployment of servers, the related paperwork, including design documents, as-built documents, and the post-deployment integration of the devices and networks that you build into your network management systems. And we've tried to automate all of these processes. And we've taken another step further in terms of not just automating the configuration, but automating the operational side as well. So this is the sort of troubleshooting that a network operations staff might do involving potentially multiple layers deep of running show commands to try to figure out what's going on when something is broken. And all the steps of that investigation process, and taking those and saying, well, instead of just applying those when network operators are trying to figure out what's broken, let's apply them all the time. Let's have systems that run these show commands and look for the patterns that the network operators are normally looking for, and then follow the processes they follow to fix things so that we can keep them from doing things that can be heuristically defined that way. And so that's neat. And is it really realistic? Well, it's a challenge, but really it's something that we've been accomplishing. It's really a matter of taking what's implicit to network engineers as humans and making it explicit in policy and code. So it's a challenge, of course, to figure out where to start. We all have operating networks. Before we started doing this, we had a very large operating network. And of course, we didn't want to throw it out. So we had to treat our running network as the authoritative resource. The network exists, it's there, it has to be the thing that we trust. So our network is our reality. And based upon that reality, then we've taken small parts of what we've deployed, and what we thought we understood as our policy, and defined those bits of policy, and then wrote systems to check them against the configurations. And we find that it's actually an iterative process. You may say, for example, on all 10 gig interfaces, all 10 gig Ethernet interfaces, you want to enable flow control. And you think that's a policy that you're going to apply across your organization. Well, when you actually check that against what's there, you may see, well, it's not true actually in a couple of cases. And that's an opportunity to either say, are those couple of cases that should be changed in configuration, or do we need to change policy to deal with exceptions, to cycle back around? And so, of course, we pick the firstly, the high impact and high frequency problem cases, and that gives us a place to start. Never define everything in this sort of process, but we do continue this cycle so that you get more and more of your configuration defined, and in fact, it's been a forcing function to make people really understand what the implications of our policy decisions they make and to decide whether or not they actually want them to be defined that way, network-wide. Has great characteristics for keeping knowledge in the network once operators and engineers are done working on particular projects and move on to other things. And it also results in really consistent, normalized, repeatable deployments, which is important in terms of getting the building blocks done that are required to deal with the rapid scaling we've been talking about. So, of course, in order to get things to that point, it does take multiple iterations to get to simple. I want to talk about a particular case study involving the history of multicast at Amazon. Most of you probably don't know that Amazon is a very heavy user of multicast internally, and we have been for a long time. About say,
7 or 8 years.
7 years ago? Yeah, we started encouraging people to use multicast as a basic transport, to make it easy to send messages between applications when you have thousands of servers. And so we made it easy for them to do that. And
the key design pattern that we were following was to let publish subscribe to happen such that you might have some interesting data, but you don't know exactly who might be interested in it. It might be a change in inventory position that occurs somewhere like in that big box in Nevada, that big building, and it might need to propagate who knows where. What we found is that both the degree of publishing and the amount of subscriptions, which drives SG state, really grew very quickly. This became very successful from an adoption point of view. That led to a lot of problems and complexity getting pushed down into the network from an operation point of view.
Yeah, so from the perspective of the developers, everything remained simple. From our perspective, things became very hectic, and so that represented a need to rather than deal with a complex system, figure out ways to drive it back towards a simplistic system so that we didn't have to think about it anymore. And in fact, specifically, we had more SG state than any other network in the world at that time by over 2 times. It's according to all information that was available then. And it was actually challenging the forwarding and state tracking potential of our vendors' hardware. And so we worked very closely with them to figure this out. In fact, we started off with PIM sparse with BSR, and eventually we found that this was getting so popular that SPT failover was getting to be quite expensive on the RPs. So we built a constrained topology that allowed us to remove SPT failover, and following that, then we found that we needed to deploy Anycast RP in order to deal with minimization of joins, and we needed to split that out eventually to multiple locations with MSTP. And these are kind of standard design evolutions for multicast networks. And we found though that about 3 years ago, even with PIM sparse, you still have to track SG state. So we were forced to move to PIM BIDR about 3 years ago, and actually we were forced to do that because of the constraints of no outage windows and that sort of things. We were forced to do each of these transitions on a live network without scheduled outages. So it's been quite a challenge, and really once we moved to PIM, and we did actually all those iterations over the course of a year once it became a problem, and really it got to simple again once we moved to BIDR, and we've been running with BIDR in our core for about 3 years now. We had to build a little bit of instrumentation around it, and then we were able to effectively forget about it. We don't worry about multicast as a major problem anymore. We still have a lot of users that use it extensively inside. Um, okay, so I mentioned originally holistic design, and we looked at the Maya graph that showed how system calls are related to each other through different systems. And I think that it's important to talk about our systems architecture a little bit to understand how we consider design holistic. In our systems architecture, we have generally homogeneous deployments of devices, of systems that are basically the same. We have rows of racks of basically the same things. And then as services are required, they're built as needed, and they're accessed through APIs. So developers can say, I need another server of that. They make a system call. They make a call to something that says, okay, give me another couple of those. It actually creates new assignments of hosts, and then they release them again when they're done with them. So to demonstrate this, so a subset of a data center here, similar racks of similar servers. We have an application red that comes online and makes a call, request for 10 units without human involvement at all. And those applications get placed basically randomly in available spaces through the data centers. And then we'll have additional applications, say blue and green will come online, and they'll make requests through similar calls. And those will be placed at random as well. And they'll add and remove them as required. And of course, in order for them to be able to make a request that says, I am blue, I need another 20 of myself out there, there has to be an architecture involved that understands how to deploy a blue. So that's one component that we've had to build here. And of course, we're dealing with thousands of different applications that are doing this sort of thing. And that leads us, from the developer side and from the system side, that this keeps everything very simple. But of course, it leads to really interesting network flows if we don't do anything about it. So I just drew a bunch of lines on here with OmniGraffle that are random but represent something that might happen. Probably it will be worse than this. And that represents something that again becomes complex if we don't do something about it. So we've had to figure out ways to be able to make this simple again from our perspective, and we've done that by creating a variety of services. Like there's a discovery service that is required to say, hey, I want a blue. What blues exist? And perhaps most interestingly, we have a network locality service, which understands the topology of the network that actually is based on the constraints of the auto deployment system that we referenced originally, that knows what's closest to anything that is querying for it, and answers by informed definition of that topology. And that all requires no people to be involved in that process as well. So give an example of network locality service, and I'll point out that NLS is a large-scale service-oriented architecture system in itself. It actually is also allocated, like all of the core components in the system, as if it was a unit of work within the entire system. So it may be yellow in one of these deployments. And as we need more NLS servers because they have a high workload, then they can also automatically be deployed into the system. And it provides a programmatic answer. You pass it a list of IP addresses, and it tells you in sorted order which one's closest to you. So that's the preference for how you should do things. Yeah.
One thing that we think about a lot is when applications meet the network, what transpires there. We do very deep instrumentation on both sides of that, and this allows application developers and applications themselves to ask programmatically, is it my problem or is it the network? And looking at it from the other direction, network tools and components can ask, is it my problem or the application? And so that we can minimize the amount of communication necessary in order to do both instrumentation, to do troubleshooting, and to do analysis. It also, we find, the more data we put together, the greater degree of correlation that we can do, and the better our visibility is into how everything is behaving. So from an application design point of view, one thing that's fairly unique at Amazon is that network engineers get to care about the application design and get very involved in it, and get to sit down with the developers and figure out, what is the application and the interaction models, and try to understand in the context and within the constraints of what's synergistic for the current network design, how can the applications that are being designed work, and what modifications are needed so that future network designs can be optimized for the new and interesting things that application developers are trying to do. So while I showed an earlier cycle that involved systems, network, mechanical and electrical engineers, there's that same synergy that we build up between systems, network, and application engineers. And we end up, as network engineers, working very closely with developers, whether they work for Amazon or not. And increasingly over recent years, we have a lot more application developers who are not Amazon employees than the number that we have who are Amazon employees. And for the ones that who are not Amazon employees but are customers building on top of our web services, if things go well, then when their CTO does his technical presentation, he includes slides like this. Don McCaskill is the CTO of SmugMug, which is a really great photo sharing site if you haven't come across it. And one of his slides is set Amazon servers on fire, not yours.
Even though that says set Amazon's servers on fire, this is also not our server on fire.
That is a very I/O intensive application, and they're very happy with how it works. Another interesting use case for what people have been able to build on top of us is something that a single developer, a lone wolf at the New York Times did, a guy called Eric Gottfried. He was tasked with getting all of the New York Times going back to 1852 and taking the 11 million articles that they had going back that time and getting them online in a useful, searchable way so that people could bring up simple PDFs of each article. And the time constraints for what he was trying to do didn't mesh with how quickly he could get servers or how quickly he could get data center space and all the usual things that you try to do to build an application. So he convinced his boss to leave his credit card on his desk and go to the bathroom for 10 minutes, and he set himself up as an Amazon AWS developer. And he got to work. He loaded all of the newspapers from 1851 to 1922 into S3, our object store, set up a Hadoop processing cluster, which works along the models of MapReduce, if you've come across that, running on EC2. He had about 100 nodes in EC2 running and processing this. Getting all the back issues into S3 was quite a volume of data. It caused, I think, the local New York Times network engineers to come and knock on his door and ask him, what's he trying to do to Amazon? And I think he said he had a loop that was running away and he'd go and stop it. Within a couple of days, he had done all that processing and generated another 1.5 terabytes of useful externally exposable data, stored that in S3, and he was done. At the end of doing all of that, he had spent $100 with Amazon, that was it, and so a fraction of one server. And one of the interesting things that he came up with in that whole search going back to the 150 years of newspapers is he came up with a computer wanted ad dating from 1892. So if you want to see what a computer wanted ad looked like in 1892, I better read it for you because it's not terribly clear, but computer wanted, Washington, May Day. A civil service examination will be held May 18th in Washington, and if necessary in other cities, to secure eligibles, eligible is a noun, for the position of computer in the Nautical Almanac office, where 2 vacancies exist, one at $1,000, the other at $1,400. That sounds like a lot, by the way. Good salary. So the examination will include the subjects of algebra, geometry, trigonometry, and astronomy. Application blanks may be obtained of the United States Civil Service Commission. The Nautical Almanac office doesn't exist in its same format anymore, so if you're an expert in algebra, geometry, trigonometry, and astronomy, you can't apply for that, but we are hiring. And I'll take questions. Good, we've got an astronomer in the room. Randy, you go first.
Well, maybe a space cadet. Randy Bush, IIJ. What happened last week?
It didn't take long, did it, Todd? We're pushing out more details over time, but basically we had what Randy's referring to is on Friday morning. We had a problem with a number of our services that impacted some of our East Coast data centers. And it was a problem that should have been eminently fixable and findable, but wasn't. And we're diving in. And, we hate to disappoint customers and have any outage of any type in any of our services. So we're diving into that and figuring out how to do future prevention.
I'm not asking for blame. I'm asking, do you have any lessons so that, all of us are in the same or varying boats? Have you learned anything yet that we could learn so that it doesn't happen to us?
I think one of the key lessons, Randy, is with respect to how you think about dependency mapping and thinking about even the most obscure contributors that contribute to providing any sort of high-level service. You need to do incredibly rigorous testing of the edge cases and of the obscure service failures, and think about how you do back-off and recovery such that the edge cases can't add up and cause anything else to tumble down at higher levels. I think it's a real challenge in a service-oriented architecture like what we've built, where a lot of the newer applications being built are mashing together different APIs, and you really have to think quite defensively in terms of
multiple failures
no,
that interact.
Actually, really single failure that had cascading effects at higher levels. So you really have to think very closely about how you defend yourself and how the edge case doesn't affect the common case of what people are trying to do. I think that's one last end. Feel free to chat to me more, Randy. Next question in the middle. Okay, go ahead.
Yes, Ann Johnson, C-Packet Networks. So I was very interested in the concept of locality and in how you decide what the, quotes, best, quotes, server might be. So would you say a little bit more about that? The slide said IP addresses, but there has to be more to it than just which is the closest IP address, and how do you define closest?
Yeah, in general, best isn't necessarily the absolute closest, because in many cases, half a millisecond doesn't really matter. And so with respect to how we provide answers, what we respond in the order of the list that you get back is impacted by available capacity, not just topological proximity. Does that help?
That helps, yes, thank you.
Another dimension of this is we're trying to figure out how to expose this to external developers, obviously, because it's something that external developers are very interested in. And we're open to input on what form people would like that to take. But one thing that does look attractive is what allows an external developer to think about fault zones and the different pieces of the topology that have the potential to fail together, and what you need to do in terms of isolation of different components of what you build so that you can be protected from some of those failures.
So you want to do some fate sharing indication. You want to say which things share fate, which things don't.
I didn't quite catch that part.
Fate sharing.
Fate sharing, yes. So you want to be able to, you want to be able to consciously make decisions about what you share fate with and how you protect yourselves from the fate of other things on which you depend.
Todd Underwood, Renesys. I'm interested in the way in which Amazon has been, for some time now, transitioning from a company that uses a lot of interesting technology to sell crap to a company that's selling its technological muck. And right, because that's what's happening, right?
Yeah.
And so what's interesting to me about that is, was that something that was always schemed about and is just now sort of coming to fruition? Or did senior management at Amazon, Bezos, wake up one day and say, hey, that's a lot of cool stuff over there, I'll bet we could sell it? And how does that impact the role that people like you guys have in your organization? Because in some companies, you guys are just a cost center and you're spending too much money.
Yeah.
And I have the feeling that at Amazon, maybe not so much anymore. So can you talk a little bit about how that happened?
Yeah, so I have an opportunity here to make our CEO, Jeff Bezos, sound incredibly prescient, and he's not. This is not part of the business plan as written on a car driving from Manhattan to Seattle 13 years ago. But what we did find as we evolved was that we had built a lot of really useful technology that only we were using. And slowly we started to, for our e-commerce platform technology, we started to have other sites like Target and Marks and Spencer's and so on would be able to run on top of that. But we found that there were very useful primitives that we could expose to outsiders. And we went ahead and did that. And our hope and expectation is that that will turn into a material business for us. And it's growing nicely. We're very surprised and pleased with how small companies are, like the Smug Mugs of the world, are starting to use that now. And they're really informing how we shape the nature of those abstractions that we provide on top of the infrastructure muck. The second part of your question, Todd, is for people who have been, as you can imagine, we had built a lot of this technology assuming that it wouldn't be exposed to some random developer who knows where. And we have had to change our culture with respect to everything we build now, with the expectation that at some point in time, it's very likely that it will get exposed, so build it with a view to non-employees and people with maybe lower connectivity to the service entry point consuming it at some point. That was a great question. Yes, okay.
Hi, I'm Dana Blair with Cisco. You're managing a lot of complex information flows in a hopefully simple way from the user point of view. Do you consider symmetry of information flow or asymmetry of information flow? Have y'all analyzed that as how it impacts meeting your overall availability goals?
You go. Well, it depends on what level. Symmetry is important for in some areas of our network design, especially where Anycast is a concern. I think of symmetry generally more as a matter of something that is applied to network designs rather than flows, though.
I guess what I'm getting at is I've seen the goals of troubleshooting and performance can have, depending on whether you're symmetrical or asymmetrical, are kind of in opposition. I was wondering if you've actually thought about that, or if you have anything on that.
I think asymmetry is like network partitions and lots of other perturbations in a large-scale environment. It'll just exist, and you have to deal with it. And
a lot of the flows that we have to deal with are fairly tightly localized, though, once they go through the lookup process. So they tend to be symmetric in the local area. Yeah.
Dino at Cisco. Regarding Randy's questions about the outs is due to edge cases. Do you see your edge cases increasing drastically, a little bit, flattening, going down? And are they at the application level, the network level, all over the place? And are you doing anything to simplify your network so there are less edge cases?
I think the Bider example is a good example of a radical degree of simplification. And like Mousy Tongue's comment about the Russian or the French Revolution, it may be too early to tell how well that's working, but it's been pretty stable for about 3 years or more. Simplicity is the first design principle that we always consider every time a bunch of people get in a room and think about a design. It's hard to get more specific than that,
Are your edge cases increasing?
I haven't trended them.
I think that probably not. I mean, we have interesting.
Maybe the question is, you probably don't know about all your edge cases until they happen, right?
One thing that does influence how we do designs is we try to do pretty rapid prototyping and provide minimal functionality early and allow the use of that early prototyping and like alpha and beta releases to influence what additional features get built over time. So we tend to not release very, very full-featured services. We strive for simplicity in the design process and have our customers influence what gets added on over time.
So let me ask you a direct question as a protocol designer. If you wanted to add new functionality to your network, would you prefer a new protocol to be added to the mix, or would you like to modify an existing protocol to make it happen? Do you have any preferences?
It depends on what we're talking about specifically. We have to look at what makes sense for the end goal and.
And do you believe more protocols increases OpEx? You have any opinions?
Generally, adding additional protocols is not desirable, but sometimes things will get to. We keep it expanding, so as we look at higher level designs and how to deal with larger and larger systems, then sometimes there's a need to go beyond what we've done before. So.
Okay, and one last quick question. So centralization versus distributed. I'm sure you guys have played that accordion either way. Do you lean one way or the other? I mean, it always pulls a trade-off with network management, obviously.
In terms of how we organize our entire technology organization, we try to be as distributed as possible and to minimize the intercommunication between teams and have as much of that communication happen through clean, hardened APIs so that people don't have to talk to each other, and ideally APIs that are pretty self-describing so that the consumer of them can just look and say, okay, well, I have a good sense of how that works. All right. Thanks very much for your time. And thanks to Josh for finally twisting our arms hard enough that they got us to come here.